cut down the substrate concentration, and this is about as low as we can go with this particular instrument. And again, we're measuring emission over excitation as a function of time in seconds, and these little blips, each one represents 2-second time intervals. 10 seconds. The instrument takes 2 seconds. Each of these dots are 2 seconds. You can hardly see them on this scale. Now, with a non-resistant cell, we're getting fluorescence in the cell. And then when we add P5C, which is an inhibitor, that increases the fluorescence. So there is something in the pump that, even though this is a non-resistant cell, and of course here's the temperature and here's the date. We're moving along in time here. There is something that's blocked. Okay, what I'm going to show you now I think is very important. You will see curves like this in a book that was written by Erwin Webb in 1964. And of course he was studying enzymes entirely. And if you look at this curve, you can see it looks just like a titration curve. What you're plotting here essentially is a relative rate, percent inhibition, which is a relative rate, against the negative log of the inhibitor concentration. And of course it goes up like a titration curve and it levels off. So the first question is, why does this look like the Henderson-Hasselbalch equation? Well, the answer is obvious. They're both based on the law of mass action, and even though these are relative rates instead of thermodynamic constants or titration values, you'd still get the same form of the equation. So the equation has the same form as Henderson-Hasselbalch, even though it refers to rates. Okay, if we increase the concentration of P5C, it goes up with the concentration. Of course, since this is negative log, the concentration is going up to the right, and it's exponential. Eventually, at 9 or 10 micromolar, the two values are constant. So what we've done now is saturated the pump with P5C and it's fully blocked. So that gives us a very important standard. We have, of course, the control is obvious. It's when your inhibitor is 0. That's by definition has got to be 0. And when you start to get points that are constant, then that's your 100% value. Now, in order to calculate this curve, what do you need? If you look in the literature, even today, you'll see points all the way up here. They work weeks and months to get a curve like this, which is ridiculous. It's a waste of time. If you know 0, and if you know the value of 100, you only need 1 point to do this whole curve. And that's the power of the laws of mass action, and it's the central law of biology. And if you understand this, it'll save you lots of aggravation. And I recommend Webb's book, although his derivations are very long and tedious. He always gets the right answer. Okay, if we go to the 50% point, this should tell us something about the I50. If we drop a line here, we'll get the negative log of the inhibition constant. And of course, then you look in the log table, and that'll tell you I50. So in other words, halfway down between from 100 to 0, of course, you'll get the negative log of the inhibition constant. Now, for our particular experiment, based on what I showed you with the cells a little while ago, the percent inhibition is identical to the percent of the retention rate. Because as you inhibit the pump, as you inhibit the pump, you will increase the retention of calcium in the same function. So that those two things are superimposable. Going in the other direction, efflux, of course, is increasing as you go down. When you have the control, no inhibitor, you're getting the maximal efflux. Okay, well, this is just some old data of mine using this. This is actually percent inhibition. It's 0 to 1 instead of 0 to 100. But if you can't get the 100% point, you have to get lots of points. and then you get 50%. This is two different substrate concentration, and this is known to be a non-competitive reaction. Okay, how do we do the experiment? We take the inhibitor at a known concentration, and we take certain concentration of CEMB-LB100 cells. This is the same cell line which is now capable of surviving in 100 nanomolar vinblastine, which is a toxic level, believe me. And so these are resistant cells. They are MDR1 cells. They apparently have no other form of resistance, according to the man who created this cell line, which is Bill Beck. Okay, and then they mixed in this mixture of buffered saline and the 1640 without phenol red, incubated at 30 degrees. The reason for this is that a lot of these drugs are toxic, and you want to try to keep your cells in good shape throughout the experiment, so they're incubated at a lower temperature just so that they'll survive the experiment. And then mild stirring for 45 minutes. This was done in an incubator. Okay, the cell suspension was then put in the water bath that I showed you at 37, and then 1.9 mil sample of the cell suspension, which contained 4 times 10 to the 6 cells. The way you know the cells is, of course, you do a cell count with a microscope and trypan blue at the beginning for each experiment. And then you place it in the plastic cuvette, stir it at 35 degrees. And then when you've got everything ready to go, your instrument is all set, you give it a squirt of 0.1 mil of ice cold calcium AM and PBS. And then you measure the rate of cellular calcium retention by fluorescence. How are we doing so far? Anybody having any trouble with this? I'm not going to give you any derivations because I know that's an absolute cure for insomnia. Okay, all of these plots will be the same. They'll also all be emission over excitation ratio, and they'll all be time in this axis. Now the time will change, the time scale will change depending on the substrate concentration. Obviously, the rate goes up when you increase the substrate. Okay, this is the control at 60 nanomolar calcium AM. The control is close to 0 in this experiment. This is the effect of 10 micromolar PSC, which we've said is 100% inhibition of the pump. So that's the fastest rate that we can get, and that's the fastest retention we can get, and presumably 0 efflux. 13 micromolar dextragolidine. Dextragolidine is a German drug which has also been developed for the same purpose, to block the pump. All these drugs are currently in clinical trial, and so the outcome will be very important for cancer patients. Okay, down here we have maximal efflux, and up here we have maximal retention. So that's what the experiments look like. Here you can see the 2-second time points pretty well. You can see little dots. And this went over a scale of 280 seconds.